This topic is Bayes theorem, very important. It's just a refactoring of conditional probability, but it's used widely. So this is Bayes theorem. So what does Bayes theorem say? So I'll just, this is just a formula, and then I'll show you something that is used. Okay. So we know that from the conditional probability formula, P of A given B is equal to P of A intersection B by probability of B. We can reshuffle this and we can say that P of A intersection B is equal to P of B into P of A given B, right? This is sometimes called as chain rule also. This is nothing but, you have seen, right? This is just a refactor. I just brought this here, multiplied these two, okay, to get this. So if this is there, so this is my first equation. Now second equation I can do the other way around too, right? The other way around would be just a minute. P of A intersection B or B intersection A, both is same, right? If you do it the other way around, this will become P of A into P of B given A. I hope we can write it this way also. You get it? This is my second equation. These two are same. A intersection B or B intersection A. Now let's refactor this. So now from this, and we know that, so this is, sorry, I'll just write the equations as we do in our maths. So this is my first equation, this is my second equation, this is my third equation. So as we say, from 1, 2 and 3, what we can say? Let's rewrite. We want to write P of probability of A given B. Now how can we write A intersection B? A intersection B is same as B intersection A. These both are same. A and B or B and A, both are same, right? So I can replace this with this thing. Okay, so let me replace this. So this will be P of A into P of B given A. This is how we read it, and by P of B. This is what is called our Bayes rule, Bayes theorem. This is what is Bayes theorem, guys. Nothing but just a refactoring of this conditional probability formula. Okay, let's continue. I'll give you one more example of this. So there's something that you should know. Okay, I'll just find it and let you know. This will be useful when, just for your understanding, when we do it later. So just for your understanding, these are the terminologies, just to introduce the terminologies I will give you. So whatever I've written, so the terms that we, instead of A and B, I hope this is visible. So now replace A with hypothesis and B with A with H and E with evidence. Okay, so A and B. So probability of hypothesis given evidence. So this is your A, this is your B, and then this formula. So probability of hypothesis is true given the evidence. This is given by probability of hypothesis is true before any evidence is present. Okay, before any evidence we have, this is the probability that we had, like 1 by 6 in the earlier case. Okay, and then we have probability of evidence given the hypothesis is true. This is your given by probability of E given H. And then in the denominator we have probability of observing the evidence. So this is the terminologies that I wanted you to know, hypothesis and evidence. So this may seem like what is it, but this is nothing but the same thing, guys. Okay, so this is a Bayes theorem, and let me give you some more terms around this Bayes theorem. So this is just good to know. So again, probability of A given B is equal to probability of A into probability of B given A by probability of B. So what are these things called? So this is sometimes referred to as, just know the terms. This is called posterior, means after getting the new evidence or the new information what I have got, what is the truth now? Well, this is the posterior. And before, this is called prior. Before getting the evidence, so this is my probability of evidence, this is my evidence, and this is called the likelihood of that event happening. This is without anything, without any information. This is our earlier likelihood, okay, and then this is the prior information, that what is the new information, okay, what is the prior information that I got, and after this information, this is the posterior. So these are the terms that you should know and be comfortable with. So these are used very commonly in machine learning, okay. So this is the thing. So I'll just give you one more example, the same example that we did, and we'll try to compute it, the same rolling a die example, okay. So now we'll compute the same thing using Bayes theorem. So again, example would be, for example, we roll a die and my A is get a 5. So my sample space would be 1, 2. Now you should be comfortable. Sample space is denoted by omega, and A is get a 5. So P of getting a 5, this is I want, this will be 1 by 6, and the B would be same thing, get an odd number. So this will be probability of getting either 1, 3 or 5, and this will be half, because half of the numbers are odd numbers. So now if we want to calculate the same thing using Bayes theorem, how will we do? Probability of A getting given B. So this is probability of A into probability of B given A by probability of B. We'll compute the same thing, okay, using this. So we know, so this information we have, this is what we need. So let's focus on this one, probability of B given A. So let's read it, okay. What is probability of B given A? Probability of B given A is probability of getting an odd number given that I have seen a 5, okay, given that we have got a 5. Probability of getting an odd number given that we have already got a 5. So what would be this probability, guys? Probability of getting an odd number, or that we have already seen a 5. So we have already seen an odd number, right? So what is the probability of getting an odd number now? So this probability will be equal to 1, because 5 is an odd number and we want to get an odd number, okay. If we have got 2, 4 or 6, then this would be 0. But since we wanted to get an odd number and we know that we have got a 5, that is the information we have, probability of B given A. So we can say that this probability is 1, that I have got an odd number for sure. And if I plug this value into the formula, so probability of A getting a 5 given that I have got an odd number is probability of A is 1 by 6 into 1 by half. It boils down to the same formula, and this will be 1 by 3. Okay. Now let's dive deeper into Bayes theorem and understand its generalized form. Okay, let me give you what am I talking about. So we know that, so we have seen this example, we have understood Bayes theorem very well. Okay, so what is Bayes theorem? P of A given B is equal to probability of A into probability of B given A by probability of B. So now if you see this with the help of a diagram, so if you try to understand this, so we can draw this. See, this is our sample space, this is our A, this is our B. Okay, so we have A, we have B, this is our omega, our sample space. Okay, so now how can we denote B here? How can we understand B? So there are two parts. This is the one B, and then this is the rest of the B. So this we know. This is A intersection B. Okay, this is A intersection B. What can we say about this part? This, can we say that, or can we write it in terms of B? This is B intersection A. And can we say this is B intersection A complement? See, this is A, and intersection of B with this is B intersection A. And whatever is outside this, that is A complement, okay, or A prime as we say. And intersection of B with that A complement, anything that is outside A, that is not A. Can we say that this is B of intersection of B with A complement? So can we rewrite B now? So can we say that B is equal to B intersection A plus B intersection A complement? Can we say that probability of B is equal to probability of B intersection A plus probability of B intersection A complement? No? Let's put this in this equation. So what does our equation become now? Probability, the same Bayes theorem, this becomes probability of A given B is equal to probability of A into probability of B given A by probability of B intersection A plus probability of B intersection A complement. I hope this is clear. Okay, we have just replaced B with this. So now if you see, the sample space is divided into two parts. Let's extend this now further. So this is divided into two parts. One is A, other is A complement. So let me show you in the diagram. So if you say this is our sample space, okay, and it's divided into two parts. Say this is, one is A and another is A complement, and somewhere here in the middle our B is sitting. Okay, so this upper part is B intersection A and the lower part is B intersection A complement. So it's just a redraw of the same thing. So this is our A, this is our A, this is the whole sample space omega. This is our omega. So I'm just drawing it in circular way. And the remaining part that is outside A, the whole of this part, this is A complement. So can we say that our sample space is divided into two parts, A and A complement? And we are telling that, and we are giving the information about B as B intersection A, and this is B intersection A complement. So our omega is divided into two parts, and this is how we can give our B. Now let's take this thought a step further, and can this whole omega space can be divided into multiple such parts? Okay, what will happen then? And then we find out the intersection of B with that. Okay, so let's generalize it, and when we want to find the total probability of B, we are doing its complement with B intersection A and B intersection A complement. And now if you want to find the total probability of B with n such parts, okay, how will that be? So let me draw the diagram, and then let me reuse this diagram. Okay, let me redraw another one. So let's see, for example, if this is our sample space, so this is our omega, and let's say this is divided into n such parts. Okay, and somewhere in the middle there is our, so this is our B. And now instead of doing into two parts, dividing the sample space into two parts, A and A complement, I'm dividing into n such parts. Let me name them. So this is A1, A2, A3, this is still AN. So the sample space is divided into n parts. And now if you want to calculate the total probability of B, how will I compute that? How shall we do that? So can we write it that B is equal to B intersection A1 plus B intersection A2, so on till B intersection AN. These are the n parts, and my intersection of B with each of the parts. Okay, and finally if I sum them up, will give me the total probability of B. Okay, and this is called the law of total probability. Okay, this is called, whatever you have understood now, how to calculate the total probability of B, first using the two parts of A and A complement and then generalizing it to n parts. This thing that we have understood, this has got a name and it's called law of total probability. Let me write it down. Law of total probability. For computing any probability, we can use this law, and this holds. So let me define it for you. How is it defined? So I'll just write overall probability of any event B. What is given by considering all the mutually exclusive, okay, ways it can occur. Okay, so overall probability of any event B considering all the mutually exclusive ways it can occur. Mutually exclusive means the part that is here, it does not overlap with this part and whatever exists in this part. So all these parts are mutually exclusive. There's no overlap. So this is one part, this is one part, this is one part, and sometimes there can be multiple within this there one parts. So all the parts of B are mutually exclusive. There is no overlap. So this is what mutually exclusive means. Okay, and what are the parts in this? So A1, and what is this? The A1, A2. What do we say about A1, A2, and AN? So these are the parts of the sample space, right? What do we say about this? A1, A2 till AN. Okay, our set of events. That will make parts or partition the sample space. Okay, that will partition the sample space. What can we say about these parts also? These, whatever the parts of A1, A2, A3 these are there, these parts are also mutually exclusive, and sum of all these parts will form my sample space. So whatever is there, so these are the two rules. I'll just write it. So whatever you are seeing this in this diagram explicitly, I'll just write it in words. So these parts are mutually exclusive because there is no overlap between any of the parts, and sum of all these parts will form my sample space. So this is what we are going to write. So the first thing is about A1, A2, N, they are mutually exclusive. Okay, that is AI intersection AJ is equal to phi for all I not equal to j. So this is called null set, and this symbol is called for all. This is general. Okay, and this, this is and what is the second part about AI to AN? Is we are talking about AI to AN, that they are exhaustive. Exhaustive means the whole, if we sum all the parts A1 to AN, they will form my sample space. How do we write it mathematically? A1 union A2 union dot 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 union AN is equal to my omega. This is my this is equal to omega. Omega is my sample space. Okay, this is what it is. This is my law of total probability, and using this, how will I write my B? Probability of B is given by sigma I equal to 1 to n probability of A of I into probability of B given AI. Okay, so how will it be? So this is summation. So if you break it down, this will be, how will it be? What is this? Probability of AI into this given BI. This is probability of AI intersection B. This is what it is, right? how did we break this down? This is B intersection A intersection. So this can be written from the conditional probability, right? What is the conditional probability? Do you remember? P of A given B is equal to probability of A and B by probability of B. And this implies chain rule. What was it? Probability of A intersection B is equal to probability of A given B into probability of B, right? So can this, in terms of probability, okay, can this be written as, now this whole terms, each term, just plug it in here. So what will it become? Probability of A1 given B into probability of B plus probability of A2 given B to probability of B, and so on, right? So that same thing is written here in the reverse order. I hope you get this point. So from the chain rule, we brought it down to this part. And now if you plug this thing in the Bayes theorem, okay, from where it came, from where we came. So now if you plug this in Bayes theorem, what will it get? What will we get if we can generalize it? So now we can generalize the Bayes theorem using this law of total probability. How will it be? Let me write it in different color. Sorry. Probability. Probability of AI given B. So probability of AI, ith. So I belongs to this 1, 2, 3, 4, n. Probability of AI given B is equal to what it will be? Probability of AI into probability of B given AI by summation j equal to 1 to n. I'll use another variable in the denominator. Okay, probability intersections part, we'll write it as chain rule. Probability of AJ into probability of B given AJ. So this is a generalized, this is generalized Bayes theorem. And this is our law of total probability. Okay, so with this, I hope this is clear. So I've just extended the theory. Okay, to summarize, we found out the probability of B as B intersection A and B intersection A complement. From dividing the whole omega into two parts, we move it to n parts, and from there we can get the total probability of B. That is called law of total probability, and we got this one here, this formula of B, that is the total probability of B, and then we can write it as in the form of conditional probability, because A given B, we know that from the chain rule, right? This is a chain rule. This is the chain rule. From there, we can write it in the mathematical formulation as this form. And the same form, we'll plug it into the Bayes theorem and generalize it. And now we get this generalized Bayes theorem formula. Okay.